So in this video, we would like to explain the classical binomial theorem. And in order to give its expression, let's just recall that we define the quantity m choose n. So here we assume that m comma n belong to the set of non-negative integer numbers. So we're going to denote it like this. To be equal to m factorial over n factorial times m minus n factorial, where again we need to define what this means. So if n is a non-negative integer number, then we define n factorial to be equal to 1 if n is equal to 0, or to be equal to 1 times 2 times all the way to n if n is a natural number. So, for example, 0 factorial, of course, is 1, 1 factorial is 1, 2 factorial is 1 times 2, which is 2, 3 factorial is 1 times 2 times 3, which is 6, 4 factorial is 24, and 5 factorial is 120, and 6 factorial is 720, and so on and so forth. Okay, so we call this the binomial coefficient. There are different notations for this, but this is a classical one. And we call this m choose n. And this is well defined if m is greater than or equal to n. And if m is less than n, we usually take m choose n to be 0, but you will see we're not going to have any immediate need for that case. So this has a very nice interpretation. So it's not totally obvious that this number is going to be an integer number, but let's just make a very small experiment. Let's see how this works. So what is 7 choose 3? So again, this is what we call this, and I'm going to explain in a second why this is true. So here we would have 7 factorial over 3 factorial times 7 minus 3, which is 4 factorial. And the simplest thing that one can do here to simplify it is to actually consider a simplification of 4 factorial into 7 factorial. So 4 factorial is the product of all numbers up to 4. So when you cancel these with their counterparts in 7 factorial, we're going to find simply 7 times 6 times 5. Okay, this 6 is not that pretty, so let's make it a little prettier. And we're going to divide this by 3 factorial, which is 3 times 2 times 1. And miraculously, you will see that you have a very nice cancellation, which tells you that this is 35. So indeed, it is a natural number. So it is always a natural number because one can show, and that's not necessarily too hard, but we don't want to delve anymore into combinatorics right now, that m choose n is, and that justifies the terminology choose. It is the number of combinations of m objects chosen n at a time. So, for example, one of the most common example here is if you have 10 people and they all shake hands, how many handshakes you're going to get. And this is 10 choose 2 because you need to consider all the combinations of 10 people chosen 2 at a time, meaning in pairs. And of course, that is going to start by being 10 factorial over 2 factorial times 8 factorial. If you do the little cancellation that we just showed, this will become 10 times 9 divided by 2 times 1, which is 45 handshakes for 10 people. Now, the binomial theorem that we would like to state here tells us how to expand a plus b to the m power. And it really tells us that this is, oops, sorry about this, that this is the sum for k equals 0 to, or let me try to be as close to the notation that I gave before. So from n equals 0 to m of m choose n times a to the n times b to the m minus n. Okay, so for example, just to give a simple example, if m is equal to 2, that tells us that a plus b to the second power. How do we interpret this sum? So it's going to be 2 choose 0 for a to the 0 b squared plus 2 choose 1 a to the first times b to the first plus 2 choose 2 of a to the 0 times b squared. I'm so sorry, the very first term, of course, should have been, that should have been a, what is it, a to the 0 b squared, and the last one should have been a squared b to the 0. Sorry about this, this is now correct. And of course, we can easily compute that 2 choose 0 is 1, so that gives you b squared plus 2ab plus a squared. Okay, this might seem a little awkward that you're used to a squared plus 2ab plus b squared, but it's pretty much the same thing. So, or for m equals 3, let's do one more example. That will give us a plus b to the third. So this will be a plus b to the third is equal to 3 choose 0 times a to the 0 times b to the third plus, sorry about this, so b to the third plus 3 choose 1 a to the first times b squared plus 3 choose 2 a to the second times b to the first plus 3 choose 3 times a to the third times b to the 0, which of course if we simplify, this becomes b cubed plus 3 times ab squared plus 3 times a squared b plus a cubed, which again should be a familiar identity. Now, despite the fact that we didn't give a proof for the formula of combinations, it can be very easily justified why this expansion is so combinatorial in nature. It's because if you consider a plus b to the mth power, then that's a plus b times a plus b times all the way to a plus b. And you can understand now that in order to multiply out this product of sums, you need to pretty much do a distributive law and choose one factor from each parenthesis in all possible ways. So what I mean by that is you may start by choosing all the a's. That will give you an a to the m. Then you can choose a from or b from the first parenthesis and a from all other parentheses, and then b from the second parenthesis, a from all other parentheses, and so on and so forth. But you can understand right away that you're getting products that whose exponents add up to m. So this means that you will have a product that will be a to the 0 times b to the m, and you will have another product that will have a to the first b to the m minus 1, and another product that will be a squared b to the m minus 2, all the way to a to the m times b to the 0th. What you have to ask is how many such products do you get? And the answer pretty much boils down to a combinatorial argument, because it's like asking out of m parentheses in how many ways can you choose n a's? And the answer obviously is m choose n. So that's why here the coefficient is m choose 0, and then the coefficient is m choose 1, and then the coefficient is m choose 2, and so on till the very last one where the coefficient is m choose m. And that pretty much is a simple combinatorial interpretation of the binomial theorem. Of course, this very simple theorem is so rich. We all know that we can construct the famous Pascal triangle and get the coefficients. I remind you that, for example, if you have a row of the triangle, then the first element is 1, the last element is 1, and all the other elements are obtained by taking the corresponding sum. So 1 plus 3 is 4, 3 plus 3 is 6, 3 plus 1 is 3. Let's do one more. First one, last one, and then you will have a 5 here, you will have a 10 here. Oops, what did I say? Let's just say 3 plus 1 is 3. 3 plus 1 is 4, I meant. And you will have a 10 here, and you will have a 5 here, and so on and so forth. And there's a very simple combinatorial interpretation as to why these numbers are obtained this way. And this has to do with the fact that if you have n plus 1 objects and you want to choose n of them, then you can single out one of them and consider, on the one hand, the combinations that contain that object for sure, which means that all you need to do is choose m objects that do not contain that, so that you can for sure append that object. And then you can also ask how many of the combinations do not contain that, in which case basically you need to just make your choice out of the remaining ones and choose all of your elements, and that gives you this formula that can also be proven quite algebraically. However, this formula is what justifies, for example, that the sum of these two elements of the row will give you this one, because if you want to interpret them, the first three is m choose is, it's 3 choose 1. And the second 3 is 3 choose 2. And what you get is 4 choose 2. So you can easily see that that's exactly the formula that on which the next row of the Pascal triangle is based. So if you begin with the correct first couple of rows, you will certainly get this way all the correct coefficients. So again, there is so much more that could be said here, but our quick goal is to just understand the statement of Newton's binomial theorem. Not because we're going to use it that much. That is also not untrue, but because it's going to give us a basis for other types of combinatorics that we're going to introduce in a future video. And that's all. Thanks for watching.